Alright, first fundamental theorem of calculus. What we're going to see is we're going to see an analytical or an algebraic approach to it, and also a graphical approach, so you can see what's happening and how we're getting the answers that we're getting. Right? But before we start that, let's actually write the fundamental theorem of calculus. Right? So the fundamental theorem says that if f of x with a lowercase f, and pay attention to that because I'm going to draw some with a capital F, and they are different functions. Okay? So if f of x is continuous on the closed interval from a to b, and differentiable on the open interval a to b. Sounds familiar, right? Is it bringing back memory? Yeah? So if these two things are satisfied, what is guaranteed? IVT? No, IVT needs something else. Which one would this one be? This would be the mean value theorem, right? So if these two are true, then mean value theorem guarantees what? A value of C on the open interval from A to B such that f prime of C, not 0, f of B minus f of A over B minus A. Or basically, I-rock equals A-rock, right? Rolle's theorem is the one where the derivative was equal to 0 for some C value, right? And that's a specific case of the mean value theorem, right? That's like saying that the A-rock was what? 0. And what's going to force the A-rock to be 0? If f of A is equal to f of B, right? Yes. Got it? Alright, so that was the third condition we needed for Rolle's theorem. Alright, anyway, so just bringing back memory. Good ones, right?
Yes, sir.
So if these two things are true, then the integral from a to b of that lowercase f of x function is going to be equal to capital F of b minus capital F of a. What do you think that capital F function represents? The antiderivative of the little f, right? The lowercase f function. So where capital F of x is the antiderivative of f of x, this little guy. Cool? So there's a couple of things that you want to check for before you start finding antiderivatives and integrating from a specific number to a specific number, right? Don't just take off on all these problems and assume that they're all continuous and differentiable. Okay? You might get pumped on some of them. So you always want to check that they're what? Continuous and differentiable, right? So for example, this one, negative 2x plus 3, is it continuous and differentiable? How do I know it's continuous?
It's a polynomial.
It's a polynomial, right? It's a line, right? Lines are continuous. And is it differentiable? If I got its derivative, it would never be undefined, right? Pretty good? Right. So we can get the integral of this, right? And it should be equal to this. But in order to do this, we need to find the what first? The antiderivative, okay? I'm going to be using another type of notation. I want you to know what it means. So if we're integrating from a to b some function, we're going to find the antiderivative first, and then we're going to put this evaluation bar, and we're going to evaluate it from a to b. Okay? That's the notation I'm going to be using. I'm going to be asking you to find the antiderivative, and then I'm going to draw this bar, and I'm going to put from where to where we're evaluating it from. And then that's going to mean, or tell you to just get that top limit and plug it in, and then subtract the bottom limit after you plugged it. You understand? Pretty easy? Think we got it? So we'll do it mathematically here, algebraically, and then we'll look at the graph so we can compare results. Other notation, yeah. Cool. Let's check it out right here. So we have the integral from -2 to 1 of -2x plus 3 dx. First thing we need to do, Natalia, is find our antiderivative. Do you remember how to do that? What was the process for finding the antiderivative of polynomial type functions? Add 1 to the power and divide by that new power, right? So let's do that. Okay, let's add 1 to this power, to this right here. -2x, if we add 1 to it, what do we get? A 2, and we divide by 2, right? Plus, this would end up being 3x, and then we would say plus what? Plus c, right? And we're going to evaluate that from where to where? -2 to 1. What we wrote right here, Alejandra, is our antiderivative. Yes? We can rewrite that by simplifying it. Some of you can already do that in your head. So -x squared plus 3x plus c. And now we're ready to evaluate it. Now we can put equals, because what we're finding is the actual value of that integral. We're not approximating anymore. Alright? So plug in, which one do we plug in first? One, right? Follow the formula. Which one did I plug in first? B, which is the top one. Okay, so top limit minus bottom limit. So we're going to say negative parentheses -1, oh sorry, just 1 squared plus 3 times 1 plus c minus, now we're going to plug in the bottom limit, which is -2. So negative parentheses -2 squared plus 3 times -2 plus c. What do you think is going to happen to those c's? They're going to cancel out. Why are they going to cancel out? Because this minus is going to end up minusing it, right? So when we're working with definite integrals, we're not going to have that constant of integration, because it's actually always going to just cancel out. Okay? So when I write the rest of the problems, I'm not going to be putting that plus c there anymore. And we understand why, right?
Yeah.
Because of this example. Alright, so what do we end up with in this first parenthesis? 1 squared -1 plus 3. Get 2 plus c. Minus, what do we end up with over here? 4, but that becomes -4, and this becomes -6. -10. Right? -10 plus c. In reality, I have 2 plus c plus 10, right? Minus c. And what happens to my c's? They cancel out, and we're just left with 1. So now let's look at what that looks like graphically, okay? So we're looking at the space that's bounded between the curve and the x-axis from -2 to 1. So if I go to -2 and I go up to 1, I'm going to draw the shape that represents that space that's bounded by the curve, the x-axis, and those limits. What shape is created? A trapezoid. Okay, we calculate the area of that trapezoid, right, to find out how much space there is there. It should equal what? 12. So let's figure it out. How do I do that? 1/2 times 3, because that's this number down here, right? Times, what's base 1? 7 plus base 2? 1. So that gives me 8 times 3. 24 divided by 2? 12. Same answer?
Where does the 3 come from?
Where does the 3 come from? The height right here. 1, 2, 3. Cool? Remember, the bases are the ones that are parallel to each other. Kind of like what we've been doing with the trapezoidal Riemann symbol. Could I have done it differently? Could I have made a rectangle here
Yes.
and then a triangle there if I didn't remember the trapezoid formula?
Yeah.
Good? Alright. Look at the next one. Same thing, all they did was change the what? The interval, right? From 2 to 5. So we already know the antiderivative is negative x squared plus 3x. But now we're evaluating it from 2 to 5. So let's practice. Which one do I plug in first? Top one, 5. So negative parentheses 5 squared plus 3 times 5. Figure out what that is. Minus, plug in the bottom one. Negative parentheses 2 squared plus 3 times 2. You're going to get 5 squared, 25, that's negative 25 plus 15. Negative 10. Here we're going to get 4, but it becomes negative 4 plus 6. 2. But then we have minus, so it becomes minus 2. So what do we end up with here? Negative 12. Uh-oh. So that means that what? The space that's bounded between the curve and the x-axis is predominantly where? Below the x-axis. It might be entirely below the x-axis, right? This one we could have said it was predominantly above the x-axis, but it ended up just being completely above the x-axis. Do we understand? So based off of the sign of our answer of that integral, we can kind of tell that information. So let's graph this one. This one's from where to where? From 2 to 5, right? So if I graph that bounded area, it's going to be this right here. So in this case, it's completely below the axis. And what shape is that again? Another trapezoid, right? Okay, so let's figure out that one. 1/2 times, what's the height, Ricky? 3, very good. Where'd you get that from? The interval, right? From right there. Times, what's my base 1? Negative 1 plus my base 2? Negative 7. Okay. That'll end up giving me the negative what?
So,
Can area be negative? No.
space.
Okay, it's the space, right, bounded between the curve and the x-axis. I don't like to say the word area because it gets a little misleading. Later on, they're actually going to ask you to find area. Okay, and then you're going to get confused. You got to remember that when you're finding that area, it always has to be a positive number. Okay? So that means if your graph, or part of it, is below the x-axis, you have to imagine that that part was where? Above the x-axis, and find that. So we would have to get the what of that function? Absolute value. Okay? Be careful. There's a difference between finding the bounded area and finding the integral. Two different options. You'll see them on your calculator. Good? A couple more examples here. Look at this one here. Now we're changing the interval. We're going specifically from -1 to 4. Still the same function, right? So we get negative x squared plus 3x for our antiderivative, but now it's from -1 to 4. For some of you, this kind of seems annoying and repetitive, but there's still some people telling me to plug in the wrong number first, right? Which one do I plug in first? 4, right? The b. So we're going to get negative parentheses 4 squared plus, I forgot the x there, 3 times 4, right? Minus, plug in the second number, so negative 1 squared plus 3 times negative. On the left side, what do we get? 16, negative 16 plus 12? Negative 4? Alright, over here. 1, negative 1, negative 3, negative 4. Times the negative becomes plus 4. So we end up with 0. if we get 0 as an answer, what does that mean?
Except the area below and
So the space above the x-axis and the space below are equal to each other, therefore they cancel each other out, right? Okay? Do you understand? So let's see what that graphically looks like. Let's see if that is true. We're going from -1 to +4. Okay, so here is what it looks like up here at the top. And then this is what it looks like on the bottom. Are they the exact same amount of space? It seems to be, right? One of them's negative and one of them is positive, right? So how do I find the area of that rectangle at the top?
Triangle.
Yeah. Base times height divided by 2. So what's the base of that triangle? 1, 2.5. So 2.5 times the height. 5 divided by 2. Right? Plus, how about the red one? 2.5 as well. But now the height is -5 divided by 2. They're the exact same thing, just different signs. So that's where we get